Thank you for the introduction. Hello everyone, I'm Yeongwoo from Seoul National University. In this talk, I will present InfiniMind, a learning-optimized large-scale brain-computer interface. This work was done with my colleagues and my advisor, Professor Jangwoo Kim. Brain-computer interface, or BCI, offers innovative solutions for patients with neurological disorders. First, it directly records the signals from the brain using a specialized probe. Second, it decodes brain signals using a dedicated processor. Lastly, based on the processor's output, the probe stimulates a specific brain region. With this functionality, BCIs can be used in various medical applications, such as seizure treatment, tremor suppression, and visual prosthesis. Among the BCI implementation variants, on-BCI processing eliminates wireless communication, making it well-suited for medical applications. Traditionally, BCIs offloaded computations to external processors using wireless communications. On the other hand, on-BCI processing handles brain signals locally. This enables low response time, stable communication between probe and processor, and privacy preservation. However, stringent power constraints for BCI processors limit their scalability. First, BCI processors must operate under a few milliwatts of power budget to prevent thermal damage to brain tissue. At the same time, they need to scale to support thousands of recording probes, and this may violate safety requirements. To address this problem, prior works integrate non-volatile memory, or NVM, which allows supporting larger-scale BCI workloads. SRAM-only systems, which store all the decoder parameters in large SRAMs, suffer from high power consumption. Therefore, state-of-the-art BCI systems, such as Scalo, integrate NVM to reduce power consumption. In practical scenarios, brain signals continuously change over time. Brain signals' shape and amplitude significantly change due to various reasons, including neuron birth, neuroplasticity, and probe drift. Therefore, BCIs must adapt to these changes to ensure accurate decoding. We can maintain high accuracy with continual learning. We consider two broadly applicable BCI learning algorithms, gradient descent and clustering. First, we evaluate the accuracy of the handwriting task over time. Without learning, accuracy gradually drops due to signal variations. However, with gradient descent, we can maintain high accuracy. Second, we evaluate the accuracy of spike sorting with probe drift. Similarly, accuracy drops with increasing probe movement without learning support. On the other hand, with clustering, we can sustain high accuracy despite the probe drift. However, no prior large-scale BCI system has supported learning. To address this problem, we propose InfiniMind, the first learning-optimized large-scale BCI system. We set 3 research goals. First, we build a learning-enabled large-scale BCI system. Next, we identify the critical limitations in the learning system. Finally, we propose a learning-optimized architecture. Now, I will explain the InfiniMind baseline, which enables learning in large-scale BCIs. We implement an InfiniMind baseline by extending the state-of-the-art NVM-assisted BCI system, Scalo. To support learning, we modify the processing pipeline and NVM controller. First, Scalo utilizes processing pipeline composed of multiple processing elements to deploy decoding algorithms. Aligning with this design principle, we add new PEs for learning and build a learning pipeline. Second, Scalo utilizes simple MVM controller tailored for inference. Therefore, we extend the MVM controller with necessary components from FTL. Due to the time constraints, please refer to our paper for full design details. Now, I will explain the critical limitations in the learning system. To understand the limitations, I will first explain how BCI learning algorithms work. First, in gradient descent inference stage, the decoder computes the output using the input from each probe. In this example, the decoder controls the device using brain signals. It receives input from the probe and computes the output to move the cursor to the position the patient intends. Then, in the learning stage, the decoder updates its parameters by computing loss and backpropagating gradients. Specifically, gradients are multiplied by input signals to update the associated weights. This process is repeated for every output, causing excessive writes to weights. Second, in clustering's inference stage, the decoder classifies each probe input into the best matching cluster. In this example, the decoder performs a seizure detection. It first receives input from the probe and compares the distance with the cluster centroids. Then, it selects the best matching cluster to classify the activity as seizure or normal. Then, in the learning stage, the decoder updates its parameters by using input waveforms. Specifically, centroids are updated by calculating the weighted average with the input waveform. This process is repeated for every classification, causing excessive writes to the centroids. To summarize, BCI learning algorithms cause excessive writes when updating decoder parameters. InfiniMind baseline must account for the unique write characteristics of MVM. I will focus on flash memory, which is the most commercially mature form of MVM. First, MVM write operation has variable latency due to occasional long latency operation such as erase operation. Second, an MVM write operation is significantly slower than a read operation. Third, each block in MVM supports only a finite number of program and erase cycles before it wears out, limiting device lifetime. Due to these characteristics, InfiniMind baseline suffers from significant performance and lifetime issues caused by learning algorithms. First, we evaluate the increased latency due to learning for each algorithm. The results show that learning increases the latency by 44.6 times on average. Second, we evaluate the lifetime for each learning algorithm. The results show that both incur MVM to wear out within 5 months. Therefore, learning-enabled BCI systems require efficient support for variable latency MVM access and reduction of slow and destructive writes. Now, I will explain the InfiniMind architecture optimizations. We reduce MVM access latency and MVM write traffic by modifying NOC and MVM controller. First, we modify the NOC to support variable latency MVM access by PEs. Scalo utilizes a static scheduled NOC using worst-case bounds of MVM access latency. However, in write-intensive learning workloads, this incurs huge overhead due to variable MVM access latency. To address this, we implement a dynamic NOC that can switch MVM connections with an interruption. This allows each PE to wait only for the actual MVM access latency. Second, we modify the MVM controller to reduce write traffic to MVM. Specifically, we suggest 3 optimizations. I will explain one by one from the following slides. First, we observe that brain signals exhibit sparse and recurrent patterns. Each neuron fires a spike only when its membrane potential exceeds the threshold, leading to the sparse nature of brain signals. Also, each neuron spike has a unique shape that appears repeatedly in brain signals, contributing to its recurrent nature. Due to these properties, we can filter out many learning steps that have a negligible impact on the decoder parameters. First, for gradient descent, the input signal amplitudes are often nearly zero due to their sparse nature. As updates associated with these signals will minimally change the weights, we can filter them out. Second, for clustering, many input waveforms are often very similar to the existing cluster centroids due to their recurrent nature. In this case, updates will minimally change the cluster centroids, so we can also filter them out. As a result, we can reduce 95% and 50% of writes for each workload with negligible accuracy drop. Second, we observed that only a few neurons are highly active during specific tasks by evaluating the firing rate distribution of neurons over time. Thanks to this property, we can cache a small set of frequently updated parameters associated with active neurons. For example, in gradient descent, only a small subset of weights associated with active neurons are frequently updated. Without a cache support, these updates are all directed towards MVM. If we insert a small cache, we can accumulate these updates and reduce the write traffic to the MVM. With this approach, we can reduce writes by reusing up to 71% of the cached data. Third, centroid compression can be used to reduce MVM writes. However, we observed that the state-of-the-art BCI compression method incurs huge overhead in learning. The state-of-the-art method, MARPL, exploits similarity across all cluster centroids. Therefore, the compression granularity in MARPL is the entire set of cluster centroids. However, learning requires small centroid granularity updates for each classification. As a result, this incurs high recompression overhead due to large granularity. To address this problem, we propose a small granularity compression method for learning. The key idea is to exploit the characteristics of individual waveforms. Unlike MARPL, which suffers from high overhead due to large compression granularity, our method enables small centroid granularity compression with significantly lower recompression overhead. Our method reduces writes by achieving 82.8% compression ratio with negligible accuracy drop. Let's move on to the evaluation results. We evaluated InfiniMind on 4 representative BCI learning workloads using large-scale brain signal recordings from humans and monkeys. Workloads include GRU network, MLP, spike sorting, and template matching. For full system evaluation, we incorporated detailed logic and memory modeling. First, we implemented PEs and controllers in Verilog. Also, we generated SRAMs with the memory compiler and model MVM with the SSD simulator. First, we show performance and lifetime improvements of InfiniMind. We begin with InfiniMind baseline and cumulatively apply dynamic NOC and the 3 MVM controller optimizations. Dynamic NOC achieves 4.3 times speedup and enables further write latency reductions through later optimizations. 3 MVM controller optimizations reduce the write traffic to MVM and achieve 5.4 times speedup and 23.5 times lifetime improvement. In total, InfiniMind achieves 23.2 times speedup and 23.5 times lifetime improvement. Next, we demonstrate InfiniMind's practicality with GRU and spike sorting workloads. The results shows that InfiniMind enables practical deployments in terms of performance and device lifetime. Now, I will summarize my talk. For wider adoption of PCIs, learning must be efficiently supported on large-scale systems. To address this need, we present InfiniMind, a learning-optimized large-scale system with PCI-specific optimizations to address excessive writes. The results show that InfiniMind significantly improves both performance and lifetime, potentially enabling reliable, lifelong use of PCIs. Thank you for listening, and feel free to ask any questions.